We're going to be talking and discussing the quantum mechanical model of the atom. And in a lot of ways, this work was started by a scientist by the name of Niels Bohr. And if you will remember back to the previous recordings, we said that Bohr was a student of Rutherford's. Rutherford was the scientist that came up with the gold foil experiment and in the model, the first truly nuclear model of the atom. And with Niels Bohr, he is credited with what they call the planetary model of the atom, with electrons traveling around in orbits around a positively charged nucleus. And the story goes that he was bedridden for a particular period of time with, I think it was pneumonia, might have been some other ailment, but he asked his fiancée to come and bring him some reams of paper and pencils, and he had a problem that he wanted to think about and attack now that he had time, that he wasn't so involved in creating experiments and doing work. And so he came up with this model of the atom, and actually he borrowed some math from somebody called Heinsberg, and this equation that he came up with calculating the energy of electrons was actually borrowed from another scientist. And we said Galileo said, "I've been able to reach such great heights because I've stood on the shoulders of giants." And so although the idea came from Bohr and the concept, he used some mathematical constants and things that came from other scientists. So he came up with this planetary model, and this model had some assumptions. First, there were no in-between energy levels. You were either in one energy level or the other, and there weren't any in between. So to reach a higher energy level, you had to absorb a frequency of energy high enough to get you up to the next level. For an electron to move up a level, certain specific frequency of energy would have to be absorbed. And they call this a quantum of energy. And that's where this quantum mechanical model comes from. Bohr model continued. When electrons fell down energy levels, they emit light in the form of energy, and we call these a quantized emission of energy. And this is kind of a cool diagram that we've got here showing these different energy levels. N is equal to 1. So the energy level that's closest to the nucleus gets a value of 1, the second one a 2, the next one a 3. And so when an electron absorbs energy with enough frequency to go up an energy level, and then it falls back down, it emits this energy of light, or energy of an emission called a quantized emission. The chemical properties of elements are due to the placement of their electrons, and so this is super important, and we'll talk more and more and more about this as the units progress. Where the electrons are in the atom really influences their ability to react with other atoms outside of their own. And so the further the electron gets away from the nucleus, the higher the energy level of that electron. Bohr's work was based on spectroscopy of the hydrogen atom, and it worked really well for the hydrogen atom, and it was able to predict the energies super well. But it didn't work on heavier elements. Once we had multiple electron systems, the math kind of failed, and so we needed a better model, and the development of that model came from some other scientists. And the wave nature, it says to accomplish this task, Bohr model and the work done of the wave nature developed by Planck and de Broglie was used to develop this quantum mechanical model. So scientists building on the work of other scientists. model is based on the probability of finding an electron in certain regions in space around the nucleus. And we'll discuss why this probability concept is so important in the following slides. And Heinsberg came up with what he called the uncertainty principle, saying that you cannot know the position and momentum of a particle at any given period of time. Particles such as electrons are so small, the act of seeing them alters their position. So if you'll recall back to the experiment done by Young in the double slit experiment, one of the things that they noticed was that when they tried to detect the electron, it changed the behavior of how the electron moved. When they turned on an energy source, light is an energy source. We learned that in the electromagnetic spectrum. That light would actually move the electron and create a different pattern of movement. And so when we're looking at the electron, we say we don't really actually know exactly where it is, because by the fact that we try to detect it alters its position. And so we talk more about the probability of finding electrons in certain regions in space than we do having the electron a fixed position. You can think of it as perhaps one of your buddies. Say you have a friend and you want to locate them on a Friday night. Well, chances are your friend may be an avid skateboarder, let's say. So the probability of finding your friend at the skate park on a Friday night is relatively high, maybe 80%. But that does not take into account that his family may have a birthday celebration, or he may have decided to go to a movie with another friend or something like that. So this friend is highly energetic, just like the electron, and you may or may not find him in the region in space or the position that you might expect him to be in. Schrodinger's equation was able to quantify the probability of finding electrons using wave functions, and so he was able to do the mathematical calculations of finding electrons, or working out the probability of finding electrons in regions in space. Quantum addresses of electrons. Okay, so Schrodinger and Heinsberg and other scientists were able to work out some a 3D picture of the atom based on probability, and they use what we call quantum numbers to do so. And there are 4 basic quantum numbers. The first one is called the principal quantum number. Notice here how it's misspelled on my slide. Embarrassing. It should be Principal. I think I copied this from someplace and they misspelled it. It should be PAL because it is the main quantum number. It's not an idea. Of course, it's an idea and a principle, but it's the main quantum number, just like the principal is the main educator in the building. So this is the main quantum number, and that should be read Principal quantum number. It tells the energy level and the size of the electron cloud. L is the second quantum number, and it's called the Zumthor quantum number, or the angular momentum quantum number. It tells the sub-energy level and the shape of the electron cloud. In the next slide, we'll talk more about how these relate to each other. But you can think of them as a street address for an electron. You might have the first part being the street name and the second part being the street number. M is the magnetic quantum number, tells the number of orientations in space of each sub-energy level. And then you have the spin quantum number, telling the direction of the electron spin, clockwise or counterclockwise. So I might take a few minutes to pause the video and to write these down. You'll need to become very familiar with each one of these quantum numbers and what they mean. And then a little later on, we'll relate this to to position on the periodic table, and energy levels and reactivity and all sorts of concepts relating to different elements. So now we are going to write a quantum number chart down, and we will refer to this to give electron addresses to specific elements, electrons within elements, and it's really super cool. So the first quantum number we're going to talk about is N, which we will call the principal quantum number. Principal, right? The main one. And this one talks about the size of the cloud and the energy level of the electron. And with these quantum numbers, a lot of times we have letters and numbers. And with the principal quantum number, we'll just do numbers. We'll say 1, 2, 3, and 4 here. So we'll talk about these energy levels, and as you go down the chart, from energy level 1, 2, 3, and 4, you get more and more energy. So the energy here increases as you go down the chart. So the next level is called the L, which is the azumphal, A-Z-U-M-T-H-A-L, azumphal quantum number. In some texts and some notations, they call it the angular momentum quantum number. And this is the shape of the cloud and the sub-energy level. And these have letters and numbers. So we say S, SP, SP, D, S, P, D, and F. And these have numbers associated with them also, and we'll talk more about writing quantum numbers later. And so they have S, we say, is 0, P is 1, D is 2, and F is 3. 0, 1, 2, and 3. Okay, so you can kind of notice a pattern here. The first quantum number has one subshell. The second quantum number has 2 subshells. The third quantum number has 3 subshells, and the fourth has 4 sub-energy levels. Subshells are sub-energy levels. So we have L, or N, L, and then we have M, which is magnetic. I'm going to back up here just for a second and talk about the concept of shape of cloud. Okay, so and we'll see in the following slides, we'll see the different shapes and a little bit better drawings, but I'll try to give you a general feeling for the shapes of the electron clouds here. So an S looks like a sphere. So this would be an S cloud. A P kind of looks like a dumbbell. And P has 3 different orientations in space, and we'll talk about that in the next quantum number. But the P can be a PX, a PY, or a PZ. I like that. Okay. X, P, Y, P, Z. The D's are a little bit more difficult to draw, so I'm going to let you see those in the following slides, but this is to give you an idea of what we mean by shape of a cloud. So the electrons will be traveling around in a cloud. So an S cloud can have 2 electrons, and a P cloud can have a grand total of 6 electrons, so 2 electrons per orientation. So that's what the next quantum number talks about. The magnetic quantum number tells about the number of orientations in space. Okay, and with these have numbers and letters as well, but we generally just draw orbitals or little circles to denote the orientations in space. So this is an orbital, and in each orbital you can have 2 electrons. Try to draw this one a little bit bigger. So notice here, with the p orientation in space, you have, or the p subshell, you have 3 orientations in space. So the S can just have one. No matter how you make an S, it still looks like a sphere, right? But the P can have different orientations in space and can be more three-dimensional. A D actually has 5 different orientations in space. I didn't draw that one because it's a little bit harder to draw. And then an F has 7. Looks like a bunch of bowling balls, doesn't it? Or cannonballs. And so with this, I'll try to separate these out best I can. And so each one of these little circles can have 2 electrons. So you have one orbital. So we'll put number of orbitals 1, 3, 1, 3, 5, 1, 3, 5, and 7. Okay. So you can place 2 electrons per orbital, and that's the last quantum number is spin. And so within these orbitals, one electron will be spinning one way, and the other electron will be spinning in the opposite direction. And we call that the spin quantum number. And it'll be plus 1/2 for up and minus 1/2 for a down spin. We just put arrows up or down within those orbitals. So now we're going to put maximum electrons, and we're going to put per subshell first and maximum electrons per shell. So with an S, you can just have 2 electrons, one spinning up, one spinning down. And for this whole energy level, for the whole first energy level, you can have a maximum of 2 electrons. So 2 for an S, and for a P, you can have 1, 2, 3, 4, 5, 6 electrons. So here you can have a maximum of 6 electrons. For an S, 2. For a P, 6. 5 times 2 would give you how many? 10. Okay. 2, 6, 10. And 7 times 2 would give you 14. All right. So now let's calculate up the number of total electrons per shell. These are called the shell, and these sometimes are called the subshell. Shell and subshells. So here, 2 plus 6 would give us 8. 2, 6, and 8 makes 18. 2, 6, 10, and 14 makes 32. And so this is the quantum number chart for to use to do electron configurations. And we start using this, and then we can switch over to using the periodic table to do electron configurations, or to write out a quantum number for an electron. Okay, some orientations. Here we have an S and a P. I'll show those to you on the previous slide. I kind of drew those out. This P here, you can have multiple different P orbitals. You can have one going in this direction, one going up and down, and then one going in this direction. And so you have a P orbital with 3 different orientations in space, or magnetic quantum numbers. You can look at it that way as well. D and F orbitals, you can see how complex those get. With a D orbital, you can be in between the axial planes and that kind of thing. All sorts of different kinds of, orientations for the F orbital.